Okay, so starting point for today is actually this repository. It was already in the invitation. So the first thing everyone has to do is to go to this repository, and you see it's just a little summary prepared for myself, for you, and there are a couple of other introductions which we already went through. And today, actually, these 204 things have been added, which are giving two little introductions to the differential equations package. And yeah, we're going to start with the 01 introduction, of course, and let's hope we have time for also the stochastics part. It's actually not so much. So the thing you have to do is to click on this launch binder button here at the top. It's not always as good recognizable as a button, but indeed it's kind of a link which you can click, and then you get to this nice binder loading window. You see the preview, and within usually under a minute. Okay, so what we're going to look at today is the differential equations package, and this is one of the oldest package in the Julia ecosystem, so at least from my experience. I've been in the Julia, I've been more active in the Julia field since 3 years, I would say, and back then it was already the most famous package from all. And yeah, it just increased a number of size and depth, so it's by now the largest package about differential equations, and really gives you access to state-of-the-art solvers, to the latest development, and also a lot of standard baseline solvers, so that you can do whatever you want in this field. So in the sense, and they describe it themselves actually, it's like a full stop solution. So if you look for differential equations, you can go here and you will find everything you need. So that's a little bit the promise. I myself haven't used it in as much depth to give you kind of the full guarantee that this is really the case. But from my experience with Julia, just using Julia as the language gives you actually quite a guarantee that this thing is hackable. In case something is not supported, it is relatively easy and straightforward to extend it to whatever you need in your own. So that's really a nice thing. And yeah, and you see here, so this is kind of the introductory field. There are a lot of things which are already supported in the differential equations package. So we have kind of standard ordinary differential equations. We have partitioned, we have stochastic, we have random, we have differential, algebraic equations, delayed, we have neural differential equations, and yeah, also combinations of these. And there's even support for discrete differential equations with this. So here's the mixed, discrete, and continuous equations. So this thing is really super powerful also in terms of optimization, but more focused on the continuous systems. Okay, so yeah, now I just clicked again on it and it started within 5 seconds. Okay, so I hope everyone of you has this Jupyter notebook, and make it a little bit larger. So there are other introductions which we went through in the user group, the Julia User Group Munich, but today it's the 04, the differential equations introduction, which we want to look at first. So you just need to control click on it, or just click on it. And so I made control click to have the other window still open. And then you should have access to just a Jupyter notebook. So who's not familiar with the Jupyter notebook, the most important thing is that you have a run button here with which you can actually execute the single cells. And you have a plus button here, so with which you can create a new cell. So a cell is kind of like a text editor, and you have many text editors here. And if you have such a Julia or just a programming cell, you can actually use it, and it's really just normal Julia. And I'm still connecting to the kernel right now, so hence I don't see any output. Now I'm connected, so it should execute in a second. And you have just standard Julia surroundings. So you can also import packages, and another way of executing things is, which I use most of the time, is Shift Enter or Control Enter. But you can always kind of just just add a new cell and run it. So that's the totally GUI way to do it, and it works. So you've kind of a ready setup, yeah. So you have a Jupyter notebook here running on the server with a lot of packages pre-installed and actually also pre-compiled, and so that things should be a bit faster. So that's really nice, and powered by Binder. So that's, yeah, thanks to that. Okay, so the differential equations package has a lot to do, and the first thing which the documentation really recommends is to go through the tutorial about ordinary differential equations. So that's the first thing everyone should have seen, and hence I just rephrased this tutorial into a Jupyter notebook for you so that you can really execute it right now. But just for you to have the background, so we are kind of having a version of this first tutorial, the ordinary differential equations tutorial. Let's make this also a bit bigger. So this is now kind of recompiled into a Jupyter notebook version, which we have here, so you can a little bit more conveniently go through it. So let's jump right into it, but to give you already a feeling, and yeah, maybe go all to the first Julia cell here, and you can click also on this little run button to run it, because the first time a Julia package loads, still some things take a little bit longer, because Julia is a just-in-time compiled language. We have pre-compilation, which improves startup times, but still there's a couple of things which just need to be compiled on the first run. And then they are blazingly fast, but the first time takes a bit longer. So what do we have here? We have kind of just an introduction to a general differential equation. So we have our target variable u, where we don't know the real formula, the equation, but we can model the derivative of this function. So that's kind of the usual approach. The real thing is a bit too complex, but we know how things change over time. So this is kind of really general approach, and you can use it to model anything like this. Yeah, super successful in physics and everywhere. But this is the general approach. So what do we have here in addition? What do we get? We define kind of our function, how things change over time, and we get as input parameters the actual values themselves. So how's the world at the time where we currently are? And in addition, we have kind of also access to some parameters. This is just for convenience, so that we can make things a little bit more general and then change just some parameters and then look at different versions of things. And the last thing which we also get is the actual time where we are in. So because we model the difference over time, how things change, it can be quite important, like what's the current time. And to begin with, we have just a very simple example that things change in a, what's this? Like an exponential manner. Yeah. So if we have the change over time is linear, so alpha is just a constant, linear to our current value, what we currently have. So if we solve this, we know that this is actually exponential function, and yeah, because we add what we already have, this gets exponential. I think it gives kind of an intuition. And how do we do this in Julia is now kind of the interesting part. So we define our function really plainly as a Julia function. So first is you import a package using differential equations. If you're new to Julia, you may be confused because there are two versions to import a package. There's the import and the using. And the using is for practical usage like an import, but it in addition brings a couple of variables into your current namespace so that you can just start and use the methods defined here. And you see that we do this right now. So we have an ordinary differential equation problem, and we have the method solve, which comes from the package. And yeah, so what we first do, and this is really nice, neat Julia syntax to define functions. We just define a function called f, which gets u, p, and t as parameters, and we use a simple equal sign to assign this to an expression, which now just has a constant 1.10 as this alpha value and multiplies it by the current value of the system. So you see that this assumes that the system now is just a single value, which you can multiply directly. We have a u0, which is like our initial world, which we start with. We start at 1/2 now for this little example, and we want to simulate our system for a time span between 0 and 1. So this we can now put into a differential equation problem by first providing the function, the starting value then, and then the time span. So this you just have to remember, but it's relatively straightforward. So you pass them by position, yeah, first makes first and second and third. But yeah, it's the usual way, and defining them or giving them names first is one of the very straightforward ways to make it very clean also from the code side, so that you see what's going on. And yeah, and finally we call the solve function, which is provided by the package, and we solve our problem with a specific solver. So this is kind of an art in itself to choose the right solver. Here we just take the example from the code. So the SID5 is one of the recommended options, but you can check out the documentation there. Yeah, there's a little art to it, but you have also just a standard recommendation. We have a relative tolerance, which can set here absolute tolerance, and this is just to give you an idea that there are really a lot of more parameters which you can adapt. So this solve is like the general entry point where you can specify a lot of things. Same for the problem itself, so you can specify further things for the problem. So you see that if we computed this, we get a solution which here prints relatively nicely. So we see that things have been successful. We have a time vector for which we computed our system, and we have our solution u, which is then our system for this time. And we get a nice little visualization of this using the general plots package. So plots is the user package for plotting. There are some other packages out there which are getting also more momentum. So the Makey project is really awesome, but yeah, the plots is still for newcomers is the go-to, and it's also used everywhere. You see it's relatively simple. So what we do here is just we activate again the plots package, and this thing, I should have made a comment here, is just to get a nice interactive plotting system in our Jupyter notebook. So this activates Plotly backend. So you can visualize plots different ways. You just can render them as PNGs, as images, or you can render them as nice interactive HTML, JavaScript combinations. And this is what we do with the help of Plotly. So then we can just use the general plot command with our solution here as the first argument, and then again with thousands of parameters you can tweak whatever you want. So here we tweak the most obvious stuff, the axis names and title and also some label. And nice thing, you can adapt, you can add to an existing plot, and the only difference is that you provide an exclamation mark in the end. So this is the Julia sign for changing stuff. So we are going to change the current plot and add a new thing to it. And what we add is here the time itself. And over the time, we plot a function. And as you recognize, this is our function, which is the optimal solution. So if we solve our system, this is the true solution. And we just plot it here as well for visualization purposes. So for a couple of you, probably this already compiled. And this is one of the biggest drawbacks of Julia, which is currently also approached. So people are working on this, but because of this focus on being both high level, interactive, and super performant with focus on throughput, we have this compilation step in the beginning. So in Python, you would see the first plot a little bit faster because it focuses on just executing the code on the fly, on interpreting it in the sense. In Julia, there are additional steps happening to make the code fast, and these additional steps are just slowing things down on the first time, which is a little bit unfortunate in this setting. But from the practical perspective, it was never a real issue for me, because as soon as you have this thing running, it's really blazingly fast. So first, enjoy the nice interactive Plotly landscape. Yeah, so we can zoom in, we can zoom out, we see a focus, and we see also that we found the right solution. And just to give you the idea, so if you execute it again, it's now much faster. So it doesn't take so long again and should give you a plot in reasonable time. So you see it's already there. So it's really only the first time you plot things which takes the most time. Okay, so we have a couple of questions. Roland asked how the time is chosen. So this depends on your modeling. So time is of course like continuously going on. So you can kind of put everything into 0 and 1, but if you have a precise timing, which let's say you want to model the last 2 years of 2 populations in an ecosystem, how they evolved, of course it would be a natural thing to use this time frame and map it there. Still, you probably would map it to real numbers, to have a better feeling, to make it a bit more appropriate for the system. But nevertheless, you give an interpretation, then 0 would be kind of start 2016, and 1 would be end 2018. That's really more based on your concrete use case. Marco asked a question, what is meant with interpolation, specialized fourth order free interpolation? We have this as an output here. So we see this in a second. At least this is my understanding of it. So we can access the solution in 2 ways. The one is just by accessing the single elements of these lists, of these arrays. So that's quite natural. In Julia, we can index into things by using the brackets, the square brackets, and the first entry is actually the 1. So you may have recognized this already. But we actually start with 1 and then count further. And we can also use just the call syntax. So we see we have our solution here, and now we use normal parentheses. And this will use the interpolation. And here the interpolation can change depending on the solver you use and a couple of parameters. You specify configuration, and giving our configuration, we get an interpolation which is actually not just linear, adding 2 things and taking the middle of it, but we have a fourth order interpolation, which is just more concrete. And we get it, so I interpret we get it for free, like it was not in addition computed, but just the process itself had to compute it anyway. So we can safely use it and don't fear that anything was way slower, because we now have this awesome interpolation. So this works nicely, and you can also check it, like here they use an index, and here you use the precise time. So if we go something near 0, so we approach, what do we approach? 0.5, it's the value, time 0 matched to 0.5. So it should be more nearer 0.5. Let's get this there, and it is. Okay, so what do we have? So just to repeat what Christoph already answered in the chat, the free stands for that it's not, it's all done with just dot products. So actually linear combination of the basis functions are enough to get the fourth order interpolation.